Hi everyone. Hope you had a good session. Yeah, I want to welcome you to the session based on the state of the art in the Semantic Web Journal. This presentation here is based on a recent work that we introduced last year. It was a survey about visual transfer learning using knowledge graphs. So the main thing is how can we leverage knowledge that we have in knowledge graph to accelerate and improve the performance of computer vision models, especially for transfer learning scenarios like domain generalization. And yeah, I'm Sebastian Monka. I'm working at Bosch as a research scientist, and the work was done in collaboration with Lavdim Halilaj and Professor Achim Rettinger. So to get everyone on board, what is a typical computer vision setting? It's having images, for example, here as an example, stop signs. You also have in supervised learning scenarios labels that come with these stop signs that can be descriptions for the different images, or for example, the class that this stop sign has. So class stop sign. And what you do is you feed this image into a deep neural network. This transforms the pixel information into the visual embedding space, so a lower dimensional vector representation. And on this visual embedding, you can process different other tasks, like you can separate these different vectors from each other, for example, for classification or not. And then you have the label and you try to learn in reverse the function between the images and the specific label. And therefore you generate a network that can detect these images on the fly. However, there is a problem with traditional or state-of-the-art computer vision systems based on machine learning or deep learning, and this is the transfer learning scenario. So if you train, for example, these networks on road signs, so this is the source domain, the training domain, then you feed this, like I described before, into the network. You learn the specific images, and you can perform different tasks like classification. If you keep the source domain, then these networks will great because they highly adapt to the distribution of the images. But if you change to a target domain, which happens in real life, then, for example, here you would have images from China or images from another distribution that you also want to classify as a lion. And then the network that you initially trained on the source domain will fail on the target domain because you harm the IID assumptions that the images are identically and independent distributed. What that means, basic machine learning cannot deal with these scenarios. So what we want to focus and what research is also focused is to reduce the strong dependency on the image data distribution. This must be relaxed. Typical visual transfer learning scenarios are, there are two forms of them. So the first one is the input domain change. You train, for example, on the source domain, but when running these networks, for example, in the car, then you suddenly have some naturally occurring changes. For example, the weather can change. There could be some artificial drawings on the signs. You have a country change. And with all these scenarios, the network should be able to deal with. But since it is a domain change in the transfer learning scenarios, machine learning approaches, they have hard problems to adapt to these things. And the task, how you name it in computer vision, is also known as domain generalization or domain adaptation. The second form of transfer learning is part of zero-shot learning or few-shot learning. This is if you change the output domain. So, for example, in the training time, you have a speed limit 30 sign or a speed limit 80 sign that you want to predict. But in inference, you will also be, or the network should be able to predict other signs, like, for example, speed limit 70 signs or other signs that didn't occur at training time. This is also a problem for state-of-the-art deep learning systems. The main thing that we argue, and also which is done by most of the systems, is to induce prior knowledge into the process, into the standard deep learning process. The following framework looks like this, that we follow and other approaches also follow, is we want to combine prior knowledge with image data, as I said before. And in visual transfer learning using knowledge graphs, prior knowledge should be stored in a knowledge graph, and the image data should be processed by deep learning. And therefore, we have this long discussion about how to combine symbolic AI and machine learning. And therefore, we can see this work part of neurosymbolic AI. But to get a first feeling about what is prior knowledge and how could prior knowledge look like, there is no standard definition. So in machine learning, we would say every knowledge that is used in addition to the image data is prior knowledge. This could be also the network architecture and so on. But here in this sense, we think about knowledge that you could encode or humans can encode into a graph. And this would be extra knowledge like the shape of the signs, the color of the signs, the hierarchy or the country, or a camera that has recorded could be automatically extracted. And there are many possibilities to encode this. And as we said, we want to encode this knowledge for convenience into a knowledge graph. And an example knowledge graph could look like this. So, for example, here the stop sign has a different type, a subclass. It has a different country. It has a different background color. It has different camera, and so on. And we also have multiple signs encoded. So every node in the graph has, or every class is encoded as a node in the graph, and therefore has relationships to other classes based on the node relationship. Why the knowledge graph? There's also more than just the convenience of encoding the explicit knowledge, because prior knowledge, as we define it, can be implicitly or explicitly encoded. Explicitly is the thing that I showed before. So the knowledge graph has the different classes included. It has the different relationships. It is intuitive. It is positional, it's symbolic. So it has all the benefits of traditional symbolic AI. But recently, there are also appeared knowledge graph embedding methods. So where you encode the classes and properties and entities into a vector space. And this is also a main benefit of using the knowledge graph. So you have the tools, you have the environment to transform the explicit representation that can be created by humans into a vector-based representation that could be used for further processings. Right, and what I mean by further processings is the embedding space in deep learning. So as I showed in the first slide, the following pipeline is from input to output. There is an embedding space in between, and we see this embedding space also in visual applications. So when we transform the images to predict on these images, we generate a so-called visual embedding space. So every individual image has a location in its embedding space. And if the image has the same meaning as the other image, so for example, it contains the same class, then this embedding will be next to an embedding of a related image. And here we define it as semantic, because it's not visual, so maybe a quite easy definition. And on this side, we see the knowledge graph. And if we have a relationship, for example, between a cat and a dog, and then this relationship will be also present based on the information and the similarity in the vector space. And due to the fact that we can encode prior knowledge in a similar format as the image information, there recently came a lot of different new possibilities to combine these both modalities and image data and prior knowledge. So when we looked for the survey at the whole landscape of combinations of knowledge graphs and visual applications, and therefore we came up with 4 distinct categories. So the first category is the knowledge graph as a reviewer. So we see the knowledge graph as a reviewer as a sequential and independent processing of deep learning and knowledge graph. So for example, you have a pre-trained network. It can be pre-trained, I don't know, an ImageNet early on, or now you have these big foundation models, and then you generate a vector based on the training data that you used for example, here this squirrel. And the thing is that you transform then the image into a symbolic representation. So for example, the output of the network is the class of the image, or the object itself, or the parts of the object. So this all depends on the network and the pre-training task. But this is the trick, to transform the image into symbolic representations. And using the graph, you can process these symbolic representations in kind of a post-processing fashion. And this is where a lot of applications combine the deep learning pipeline with the knowledge graph. However, when we look at the transfer learning scenarios, this is not a very promising approach, at least what we can see. And the reason for that is that the visual features in transfer learning scenarios change because the distribution changes. So what happens is that the network is not able to detect the correct symbolic output. So for example, it doesn't detect any ear or any eye of the animal, and therefore all the post-processing is useless in the end. And this is what we saw so far. A second one is the knowledge graph as a trainee. In contrast to the knowledge graph in the beginning, it's a parallel training process. So we have in the upper part, we have the transformation from the graph into the semantic embedding, and on the lower part, we have the transformation from the images into the visual embedding. And if you keep both networks as it is, so both are pre-trained independently, and you just learn these transformation function here to align the semantic embedding to the visual embedding, then it's called a semantic transformation model. And if you retrain the whole semantic visual feature extractor, which has a lot of benefits, then we call it a semantic visual feature extractor, of course. So the trick is you have your pre-trained visual embedding, and what you learn is you learn to align your nodes of the prior knowledge to map the visual embedding itself. And this is really prominent for output domain change. So for example, zero-shot and few-shot learning. And the trick here is that these semantic feature extractors, so for example, graph neural networks, can be easily extended at runtime with new nodes. For example, if you know the visual embedding of a horse or a doe, then you can easily extend it with a zebra. You have relationships in the graph to a zebra, and therefore you have a feeling about how should the visual embedding look like. And then if you feed a zebra and compare it to the semantic embedding of the new zebra, then you are able to detect these new classes. The knowledge graph as a trainer is the third category that is used. And this is also a parallel training process. It looks quite similar, but now it's the way around. So it's the reverse one. We don't adapt the semantic part, we adapt now the visual part. And it is seen that these reverse one, the knowledge graph as a trainer, is quite prominent in scenarios where we have input domain change. So what we want to achieve is we want to train the lower part, so the visual part, with a more independent process. And by having information from prior knowledge, we are able to lower the dependency of the images. And yeah, so for example, if you feed the squirrel, normally the visual embedding space is just formed by the distribution of the other images that are in the data set. But by having the semantic embedding as a lookup, the network is trained to align to the new positions given by the prior knowledge, and we achieve independence, or at least some independence and regularization to the image data. So what we see is that the visual features are learned based on the relationships in the prior knowledge, and the dependency of the training data is reduced. The fourth category is quite easy to explain. So as you can see, we have adaptations in both directions. So the loss function is on one hand influencing the form of the semantic embedding, but it is also influencing the training of the feature extractor to the visual embedding. And these approaches are quite prominent, of course, in both scenarios. So you can do the zero-shot learning task, for example, or the domain generalization tasks. But so this is the good thing, it improves the optimization, so you don't have these hard constraints anymore from one side to each other, because embedding space from different modalities, they look a bit different. But it also has a lot of dangers, so it loses a lot of interpretability, and it's also difficult to assign the right and correct hyperparameters. So how much should the visual embedding influence the semantic embedding, and how much should the semantic embedding influence the visual embedding? So these are many open questions in these networks or approaches of that category. If you look at the survey, which I would like to encourage you, is that we have a list of all the approaches that fall into these different categories. We also showed the different transfer tasks and others, and I think it's quite interesting to have a look at that. Also, one part of the survey is focusing on generic knowledge graphs. So what kind of knowledge graph exists? How do they look like? What kind of tasks have they been used for? You can see WordNet is used a lot in the past, but we saw that WordNet is quite limited. There are many more resources. Knowledge graphs are not that known in the field of deep learning and computer vision. So it would be nice to develop more methods and to explore more things and use them. There are also data sets. So if you think about taking a data set, for example, with images and additional attributes, you can also think about images and multiple languages, knowledge graphs, and apply them, reuse knowledge graphs, gather all the information, and so on. The survey also identified research gaps. So, for example, a big question in all the approaches is the relevant knowledge. So what kind of knowledge is relevant? How should the representation look like? We have, for example, directed labeled graphs. We deal with hypergraphs, hyperrelational graphs. But for now on, all graphs are just thrown into it. We just have one edge, and there is much more potential to explore these different graph models and types of knowledge. We also have evolved knowledge. We could integrate, aggregate, how to reuse the knowledge best of heterogeneous sources. We have also different knowledge embedding methods that need to take these different models into consideration. We should exploit the effect of different knowledge graph embedding methods, for example, transductive, inductive, supervised, and unsupervised. And also, when we look at joint embedding learning, we need to think about how can the different modalities best influence each other or the other way around. So to conclude the talk, and I think also the time is quite to an end. So we presented a categorization for visual transfer learning using knowledge graphs with all these different 4 categories. So the knowledge graph is a reviewer, the knowledge graph is a trainee, the knowledge graph is a trainer, and the knowledge graph is a peer. We also analyzed more deep into in the paper the effect of the different categories, their properties, and compared them with each other. We described the different generic knowledge graphs and relevant data sets for the field of visual transfer learning using knowledge graphs. And we also analyzed the different research gaps that are present for a good visual transfer learning using knowledge graphs. Yeah, I hope it was a quite fast one. So thanks all you for your attention. And if you have questions, then you're welcome to paste all these things in the chat, and I will happy to answer them. Thank you. Of course, if you have no questions right now and you're just interested in the topic, you're also welcome to write me on my email. But we can do a follow-up if there are some research projects also in the same direction. I'm also happy to continue a discussion. I guess there is a lot of potential, and right. So there's a lot of potential inducing prior knowledge into the process, and I hope that we can bring this to good results. All right, then thank you everybody, and wish you a nice conference. Have a good one. Bye bye.